Okay. Guess you can hear me. Okay, good afternoon, everyone. I'm Louisa, and I would like to present my recent research in self-reconfigurable soft rigid mobile agent with variable stiffness and adaptive morphology. Land-based mobile robots are probably the most explored and the most exploited robots nowadays. There's a big variety of their design and locomotion modes. They can be wheeled, they can be legged, they can be like a caterpillar. And the choice of their design is mainly dictated by the desired tasks and applications, which also present quite large variety. Mobile robots are so popular because they're autonomous, they're precise and stable, they're maneuverable, fast, and also they can interact with the environment and provide feedback because they're equipped with sophisticated sensors. However, it seems that mobile robots have reached the maximum of their development in terms of the hardware, because there are intrinsic limitations which are common to all conventional robots. So they have rigid structures and the links with constant shape. And the rigid structures are known for unsafe interactions with humans and objects because they are too harsh and they can accidentally damage delicate tissues. They often fail when colliding with the surroundings or with the other robots, and they cannot adapt to the changing environment. Coupled with constant shape, such robots are usually constrained to some specific locomotion and some specific application. So when the environment or the tasks are changed, this means that we need to redesign or just to make a whole new robot, which is, of course, not convenient. So soft robots have been introduced in order to solve these issues, and they did demonstrate pretty good performance due to their intrinsic adaptability, because they have deformable bodies, so they can adapt and conform to the surroundings. They can handle delicate objects, and also they're robust in the sense that they can withstand external impact without breakage. But they have lost all the benefits which are provided by the conventional mobile robots. So first and foremost, they are not autonomous. Most of the existing mobile robots require quite bulky actuation systems. They're slow, they're not precise. Also, flexible electronics is yet not developed enough, so they cannot provide them with the good sensors. And also they are pretty hard to model and control. So here is the question which arises, is it possible to leverage both paradigms and combine advantages of rigid robotics and soft robotics into one single hybrid robots, single robot, while eliminating their contradicting features? We want to have a robot which is autonomous, which is capable of free motion on a plane, relatively fast, which can undergo flexible deformation and adapt to the surroundings and handle delicate objects. Also, we want this hybrid robot to have controllable stiffness, because there are many cases when one state is more preferable over the other one. So it would be nice if we could switch between completely rigid and completely soft states, or talking more strictly between completely rigid and hybrid states. So the question is how to implement it. Here is the quick review of the state of the art. There are not so many examples in the field because it's relatively young, but there are hybrid robots with adaptive morphology, which is mostly used to switch between different locomotion modes. So on the left side, you can see a robot that can change its cylindrical shape in order to roll over different slopes. The robot in the middle utilizes reconfigurable wheels, which are round on the flat surfaces so that the robot can gain the maximum speed. But when it needs to traverse stairs or uneven surfaces, the wheels are transformed into legs. Mobile robots with variable stiffness examples there are even more limited, but there is a recent research which you can see on the right side. So this is a modular robot which consists of many rigid units attached together by a flexible loop, and this membrane can increase its stiffness by applying layer jamming technique. So this robot can move on the plane. It can, not very fast, but still, it can resemble different geometrical features. It can adapt and conform to various objects. But in our case, we want a single deformable robot that potentially can be a part of self-reconfigurable multi-agent system. In this case, you can see that the number and the arrangement of these rigid units is predefined, so they cannot assemble and disassemble themselves. Here you can see our proposed solution. So we call this robot 2S array, which stands for self-reconfigurable soft rigid agent. And it consists of 2 locomotion units connected by a variable stiffness fiber. So locomotion unit is responsible for the motion. It is equipped by 2 omni wheels on each of the unit, and they also carry all the power and electronics. This approach ensures that this robot is autonomous. And a variable stiffness fiber serves as a toggle between rigid and soft states. We make this phase transitions via LMPA. It's low melting point alloy, and the remarkable feature is that they can be molten under relatively low temperatures. So we have a nanomelt wire. When we apply the current, it generates heat and melts the LMPA, which the outer layer of it. And then it becomes liquid, and the whole structure is encapsulated by a silicone tube. So this liquid metal stays inside, but in this case, it becomes soft and we can change its shape. Right, so basically, like at the room temperature, it is rigid, and when it is hot, it becomes soft. Here you can see a schematic representation of our robot. So please note that we work with different frames. So we have B0 frame, which is a main body frame. Also, there's B1 and B2. These are frames which are attached to the segment ends, and B0 is attached to the middle point of the connector. I forgot to mention that you can fabricate such fiber in different ways, but for our experiments, we made the fiber made from 2 segments. It decreases the complexity of the fabrication and the control. And also there are 4 frames for the wheels. So basically, also one remarkable feature here is that this robot stays omnidirectional regardless of the shape of the fiber. And when the fiber is fully rigid, so this whole structure acts as a conventional omnidirectional robot. But when 1 or 2 segments are soft, then the units can move almost independently. And in this case, the robot is not just translating on the plane, but it also simultaneously undergoes the shape deformation. And in this case, we have pretty interesting not conventional motion modes, which we analyzed and try to describe in our model. I will show it next. And before we started our analysis, we made several assumptions. So first, the fiber segments are inextensible, so they can only bend, but they cannot elongate or shorten. And they strictly bend into circular arcs with constant curvature. Also, as I mentioned, we assume that units do not affect each other that much. So it means that, let's imagine one unit is kept inactive and the second one is bending the fiber. So we would assume that this inactive unit is stationary, which is, of course, is not strictly true because there is some disturbance and this unit is dragged a little bit by the moving unit. But later I will show that we mitigate this disturbance and the error is not that significant. Also, the third point, which is also very important. So in our bending, we use only lateral wheels, which is like the wheel number 1 and number 4, and we ignore the proximal wheels number 2 and number 4, because if you can see, like the axis of rotation of the second and fourth wheel, they're perpendicular to the origins of the fiber. And because of that, they mostly promote free rod deformation. And free rod deformation is quite difficult to model, and they require much higher forces, which are currently not feasible with our design. So because we have a robot which incorporates two different natures in itself, so the logical question was how we're going to describe their behavior and how we are going to put all of those things in one hybrid unified model. So we started from analyzing the wheel configuration matrices. So we have some wheel velocities which we can control, and we have output the robot velocities. And we divided this problem into, let me just put it like this. Yeah, so we divided this problem into two parts, one for when the robot is fully rigid and when it is soft. And when the robot is rigid, so we have forward, lateral, and angular velocities, which are calculated through the body frame. And you can see like this is how we define its configuration matrix, which are derived from conventional model used, generalized model used for wheeled robots. But when it is soft, so our velocities V1 and V2, they correspond to velocities of segments when they traverse some curve on the plane while bending the fiber. And its configuration matrix is defined the following way. So wheel velocities are proportional to the velocities of their units. And as we mentioned, we consider only the first and the third wheels. And so we assign zeros to the second and the fourth one. And but again, there is a question. So how we are going to combine these two different configuration matrices into one hybrid matrix? So to do that, we introduced a Boolean stiffness variable for each fiber segment. So when the segment is soft, bar sigma is equal to 1, and when it is rigid, bar sigma is equal to 0. So here you can see our result, and you can notice that at any moment, only either the first two velocities or the last three velocities can be non-zero, which makes sense because they represent different natures which cannot exist simultaneously. In this case, we end up with 12 unknown variables. So these three variables, they are orientation and positional coordinates of the wheels with reference to the body frame. And they are unknown because the shape of our robot can change. And in this case, we need to choose how we are going to estimate the shape of our robot and how we are going to retrieve these variables from the shape. So we started from those variables which we have. So the wheel coordinates with respect to the associated segment ends, they are constant, and we know them because these parts, they are rigid and that shape doesn't change with time. The only question was how we're going to map it to our design coordinates. So for that, we derived a transformation, linear transformation that maps the frames of the segment ends to the body frame based on the soft robotic R model, which uses constant curvature approximation. So the next step is to define our generalized coordinates and to find the Jacobian matrix that would map the robot velocities into these generalized coordinates. So again, we divided this problem into two sections. The one is for when the robot is omnidirectional, and here we use a conventional model with the three generalized coordinates, two position and one rotation. And in this case, Jacobian is just equal to the rotation matrix. But for shape deformable mode, we needed to come up with something new. And to analyze that, we divided this mode into three submodes, which have some common pattern in their motion. So the first option is when one segment is soft and the adjacent unit is moving. Segment is soft and the opposite unit is moving. And the third option is when both segments are soft. So we started analyzing how these units move when some of these segments are soft. And we made the simulations, assuming also, as I mentioned, that the arcs can bend into circular arcs with constant curvature. And we noticed that the path which is traversed by the unit resembles greatly logarithmic spiral. You can see like this is the first case, and this is the second, and here it resembles the logarithmic curve even more. And yeah, the same can be seen for the third option when both segments are soft. So we analyzed this and we tried to fit the logarithmic spiral to these paths which are traversed by the units. This is how the logarithmic spiral is defined, and we found out that the spiral parameters have strong correlation with the features of our robot. So basically, the parameter B is constant for all three cases, and the parameter A and the coordinates of the spiral center, they depend on the length of the segment. Also, we found the correlation between the spiral angle theta and the segment curvature kappa. We just basically mapped these ranges for all three cases. And then we supplied these parameters further in our model to derive a unified Jacobian matrix. So the rate of change of the spiral theta is proportional to the velocity of an object which traverses the spiral. So by substituting angle by curvature, we came up with, we call it like some capital kappa coefficient, and the same applies for the orientation of our body frame, which is proportional to the curvature. Yeah, for also, like, as I mentioned, like in this case, we have 5 generalized coordinates. So these are 3 generalized coordinates from the rigid state in additional 2 curvature values for both segments. It was a bit more tricky to find the coordinates, positional coordinates. So for that, we considered these 2 points, G and F, and G is the connection point between this segment and the middle link. And it lies on the logarithmic spiral, which we defined as the number 1. So we can find its position because we have spiral center and also the curvature, and the position of the F, which corresponds to the origin of the body frame. So its position relative to G is constant. So applying this linear transformations, we found our coordinates of F with relative to the global frame. So differentiating these linear transformations and applying some additional denoted coefficients, so we came up with our final Jacobian matrix for the robot in the soft state, and then we just concatenated the Jacobians for the rigid and for the soft states. Here you can see how we control our robots. So our controller consists of 3 main blocks. There is motion planner, wheel driver, and stiffness controller. On the right side, you can see the description of our motion planner, and basically it is designed as a gradient descent. So at each moment, we are calculating 4 hybrid Jacobians and corresponding configurations. So 4 because we have 4 modes, omnidirectional, and 3 shape deformable modes. And from those configurations, we're choosing the one which promotes the minimum Euclidean distance between that configuration and the target. But here we should note a very important thing, that if we use this algorithm as it is, very often we end up with the situation when the stiffness is changed quite frequently, and this is highly undesirable because phase transitions, they take time, and we don't want it. So we just implemented some additional conditions. So we undergo the phase transitions only in that case if the current motion mode cannot provide change of the configuration any further. So let me show the results of our experiments and simulations. So we conducted 5 experiments with different initial and target configurations. And as I'm in our case, so the maximum phase transitions, I think they were from 2 to 4 probably. So in general, that was okay and showed pretty good similarity with our target. We speed up just the phase transitions. So here you can see the quantitative results of those experiments. So probably the best fit is provided by the curvature, because in the algorithm tends to decrease the error faster for it, but the error is not also that big for X and Y, it just seems so because of the scale. It's like on pretty small scale for that. Also, we analyzed if the constant curvature approximation is indeed applicable for our robot. So we used a thermal camera to extract the shape of the segment. And when we extracted the median curve and calculated curvatures in each point of the curve, and you can see the comparison of the constant curvature approximation and the curvatures which we extracted. So obviously the error would increase with increasing curvature, but it stays in a reasonable range. So we can conclude that constant curvature is an adequate representation of the segment shape. We also made 2 experiments with objects handling. This example shows how the robot conforms to some object with cylindrical shape. So yeah, it looks something like this. And the other example shows the object's manipulation. The idea is the following. So the first robot just approaches the target object while it is rigid. Then if needed, it undergoes some deformation and tries to grasp that object. We can still manipulate it while the robot is being soft, but probably just it's more rational to do it while it is rigid, just because you can apply bigger force because it's rigid. So yeah, similar experiments can be done with some other shapes. So this is it, and this robot showed pretty good performance in leveraging these 2 different natures of soft robots and the rigid robots. Just like one drawback which we wanted to solve next is that because we're utilizing Fields metal, the phase transitions are time consuming, which is, well, would be not convenient when we have many of them. So just the solution of one task would really take time. So we want to try to substitute this technique with some origami-based technique so that we can use maybe some mechanically controllable means for that. And in general, because we want to use this unit as an agent of self-reconfigurable system with many items, we need to simplify its design so that it would be scalable and easier to recomplicate. Yeah, and also the final step would be developing this modular system with many of these 2 SRA agents. So that's it. Thank you. Okay, any questions? Yeah. Which one? The first one, this one. The strength similarity is very high. How can you which match you evaluate the strength? Well, so we first conducted the experiments with the same initial and target configurations, and we end up with the sequence of configurations. And we also measured the configuration in real case experiments so we just had a camera and Aruka markers, and we also have some sequence of the configurations, and then we just compare them. We used, this is something called as, this DTW distance, by which we evaluated the difference between two curves. So we built these curves for each of the configuration parameter, and then we calculated the difference between them. Yeah. We also compared like the whole sequence. Mm-hmm. Yeah, this one. Yeah, so this delta Q, it's like the current configuration minus the target configuration. So I just normalize it because it would be difficult to represent because they took different amount of time. So they just like, it's very difficult then to differentiate. Mm-hmm. Mm-hmm. Not, well, in the video, it's not that obvious, but in the paper, I did specify that we have a target. So we just deformed the robot manually, placed in the target, measured the configuration, and then supplied it to the model, and then put the robot into the initial configuration, and then start the experiment. Yeah, here the target is the one that has been measured in the beginning, not the one that the robot finally ended, because you can see like it actually doesn't hit zero. So there is still some disturbance because we also like use some threshold, because if we try to reach really zero, then it just in constant stiffness changing, because I always try to switch between those shape modes, just it basically because of this thing. So it's difficult to come very close. Mm-hmm. 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 Yeah. Mm-hmm. Well, I just have some ideas which I'm trying to implement right now. Yeah, but just as Jose mentioned, because I want to use a mesh, so there might be some difficulty in modeling. So I'm thinking right now how to also to simplify this thing so that we would not end up with something even more difficult than what we had before. Mm. Yeah. Mhm. Well, I mean, like as I showed in the last experiment, so if you have a rope, then you most likely won't have enough force to exert on the object when you want to manipulate it. So the soft features, they're used mostly for interactions and for deformation, and rigid, they're used for force exertion, for the motion, speed, and autonomy. Hmm? Recoursing. Well, the target configuration of the robot, yes. And well, the robot also can perform different motion while being soft, based on those three models which I demonstrated before. So yeah, just because this is the first research in this area, so we haven't explored that much what it can do otherwise, I mean, like beyond what I have demonstrated here, but we think that there are some perspective. Mm-hmm. Well, yeah, mostly because of this, and because we are using this kind of the fiber, so it's feasible for you know, to constrain the motion of the units when they are soft. Because for instance, like if that's a rope, then the units, they actually have almost the free motion on the plane. Otherwise, for instance, like when they are like tagging or pulling each other, etc., so it also will constrain, make some additional constraints. But because we just limited the deformation to the circular arcs, which are feasible with this current design, it's also a bit easier to model it. Mm-hmm. Well, yeah, this is also something to explore for us. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Well, yeah, yeah, yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. But that's the main difficulty, to make it simple. how, how to make it simple? Mm-hmm. Okay, thank you.